Hi there, as promised, here's the second part of the transistor tester video. The first part dealt with the building of the kit. If you have not seen it already, I put a link in the description. This one is about changing the firmware. My original kit had firmware version 1.12k in it, which you can see when doing the show data command. It would be a good idea even for Windows users to set up a virtual machine running Linux, because you need that for compiling the transistor tester. Using VirtualBox, creating a Linux VM is easy. This here is a freshly installed version of Linux Mint, but other Linux flavors are of course available. First thing is to install some development tools. This here is actually from installing the programmer software, which isn't part of the transistor tester, but we need some of them anyway, and the rest doesn't hurt. The commands are available in David Griffith's Github page, and I leave a link in the description. How to actually read from or burn new firmware back into the chip and setting fuse bytes is the topic of another video, which I link into here and in the description below. As you would expect, before trying new stuff, I tried to read the content of the original chip to make a backup, and the programmer created the expected files called code for the flash memory, data for the EEPROM part, and config for the fuses. But the code and data were all just filled with hex FFs. The reason is that whoever programmed my chip set the lock byte in the fuses to prevent the content to be copied. The only option is to completely erase the chip, code and data and fuses, which will allow you to program new firmware, but the old content will be lost. This is why I strongly recommend getting yourself another RTmaker 328P. These chips are not expensive. Set aside the original and use the new one for testing new firmware. That way you have at least one version that works and can use the other to try out new stuff. At least that's what I'm doing. With that out of the way, let's proceed by cloning the transistor tester. The first command actually just creates an install directory and a few scripts. The makefile is obviously used to deal with the downloads of the actual sources. So let's run the make utility with the tt-s parameter to get the sources. Off it goes and downloads some stuff, and then stops with an async error. Long story short, the script expects a git directory which I don't have. I could create one, but instead I decided to simply change the script. And rerun the make tt-s. And after some lengthy download, this time there's no error. And I did the same fix for the documentation download. After the installation, we have a couple of new directories. The transistor tester documentation containing, documentation in a few languages. The transistor tester directory containing older and other versions, more about that in a moment. And the my tester directory, which is the latest version from Karl-Heinz Kübler. That, in turn, has a whole bunch of directories for different hardware versions and the actual source files. I know from looking at the documentation that the Mega 328 color kit appears to be for a tester that looks very much like mine. This one contains a makefile, which one can use to create that version, but there's also two already compiled and ready to burn versions where .eep refers to the EEPROM content and .hex to the flash. Let's test the OrigChina files. To do that, I created a new directory called test and then copied the EEP and hex files of that version. Of course, we also need a fuse file. For that, I copied the one that was created when trying to read the chip. It has the right format. All that's needed is to change some values. I also recommend changing the lock byte to FF so there is no copy protection. Using this programmer software called MiniPro, you need to always issue first a command to erase the chip and then program the new content, EEPROM, flash and fuses in 3 individual steps. The sequence in which you do these last 3 steps does not matter. The Windows software for this programmer has just one command that does all steps in one go. But there you need to load the source files into special buffers first. Anyway, either method works just fine. With that done, it's time to move the chip from the programmer back into the tester to try it out. Make sure no pin gets bent and of course insert it the right way. For the LCD screen, double check the pin alignment. It's very easy to shift pins by one and then scratch your head why nothing works. Ask me how I know. Anyway, woohoo, it works. Well, okay, but it's only using 4 lines of the display. The menu items look pretty similar to what came with it, and this is indeed the same 1.12K version. That is of course not exactly progress. So I erased the chip and programmed it with the code and data from the other set of precompiled files in that directory called Mega328 Color Kit. The process is exactly the same as before. The background is dark blue with white text, which although nice on the camera, is really hard to read in reality. We've got more lines in the menu, and moving it to show data, we have 1.13K, which is in fact the latest K version at present, around 1 year old. Moving on to the icons of the components reveals that they are drawn in some kind of reddish gray on dark blue and practically invisible. Again, the camera does not show how bad it really is. But there is an extensive makefile in the Mega328 Color Kit directory, which I choose to edit to fix these issues. I marked my edits with my name, which is a good habit because it helps redoing these edits when a newer firmware source version with a brand new makefile arrives. First change is to set the background from dark blue to black and the icon color to poor green. The format of the color word is shown in the comments, and hex 07E0 zeros red and blue and turns green to full intensity. To make the icons even more visible, I turned on a thicker layout, and that's all I changed. Now, to compile the source code using the new makefile, we need to install some additional packages. I forgot to capture that on video, but going back up the window, you see the command line right on top. These are the packages recommended by the makers, and I put them in even though I won't be using all of the stuff. For example, AVR-Dude, which is a tool to program chips using the USB-ASP programmer. USB-ASP is really an in-circuit programmer and not very convenient if you have socketed chips like with my tester. With that done, it's time to compile and build a new firmware which just needs the command make. It does go fairly quick, and now we have 2 new EEP and hex files. But it's worthwhile to look at the output for a moment. The important part are these percentages of memory used. So this uses 96.3% of the 32K flash memory, 10% of RAM and 85.5% of the EEPROM. So from the flash and EEPROM space we are nearly maxed out. It is possible to enable too much stuff in the makefile and you get over 100%. If that happens on either value, there's no point of burning this into the chip because it won't run. But for this run we are okay. And let's see if the changes worked. The background is black and the menu much easier to read. The icons are green and stand out. This version is quite usable and an improvement over the one that came with the kit. I put the makefile as well as the EEP and hex files on my Github page if anyone needs them, link in the description. Now I have to tell you that Karl-Heinz, who does the K versions that we have seen, has a collaborator called Markus who has created his own very different versions identified by the letter M. He seems a lot more active, and 1.45M was released in late December 2021. It turns out that Markus has just released 1.46M in time for me making this video. It is so new that it wasn't yet included with the get all the sources command I did earlier. Hence I needed to download it manually. There's a massive readme file of over 100K which is required reading because it explains what all the options for adopting it to your hardware are and what nice tools and functions you can enable or disable for the menu. There is way more stuff there than what the K versions offer or what the Mega328 memory can handle, so this is where you really have to prioritize and watch these percentages closely. The configuration option Markus offers go beyond makefiles, so here you are actually editing C header files, mainly the config.h, and since this is for an Mega328, the config_328.h. So the first order of business is to make copies to preserve the originals. I edited both configs and also showing the content, and my edits is a bit long. Bear with me. If you're planning to do this yourself, it's probably useful. If nothing else, it gives you an idea of what is available, and with every new version, the list is growing. Starting with the config.h, which is more like a shopping trip. Since my tester has a rotary encoder, I want the hardware encoder option enabled. It turns out that the other options for the encoder are correct, so no need to change. The next change is that my tester has a 2.5 volt reference, so I enabled that and also the voltage it produces. This you have to measure yourself on your hardware, of course. In my case it was 2.499 volts. I quite like to be able to measure z-diodes, so I enabled this, and the standard resistor values are close enough for my board, but if necessary I could have measured them and entered the real values here to get more accuracy. My kit had only part of the Zener circuitry, so I have to select the unswitched option. More about that later. I leave the voltage range for Zener measurements as it is. Another limitation my kit has that I don't have components necessary for the extended frequency counter, so the basic one has to do. Eventually I want to play around with a ring tester to test transformers for shortened windings, so I enable that option, but I assume I will have to use probes. I decided not to enable an event counter or the LC meter for now, because that needs quite a bit of add-on circuitry. And I also pass on the logic probe function, buzzer, and a whole raft of other stuff. For the PWM generator I decided to stick with a simple one, but I want inductance and ESR measurements. I pass on rotary test encoders, enable the square wave signal generator. I pass on infrared decoder and encoder tools and decided not to test optocouplers either. I do want unijunction transistors with or without Schottky clamps. Pass on servo testing and a bunch of one-wire devices. But I do like to test capacitors for leakage. And I turned on all combinations of resistor, capacitor and inductor testers. You can enable additional stuff for that, like displaying the color codes and tolerances against E24 or E96. I tried that once and it works, but it needs a lot of memory, so I turned it off again. Now we are into some user interface stuff. I left most of that at default settings, but I enabled auto hold. I later realized that just means you have to press a button for every measurement, so I turned that off again. Besides, I think you can toggle that by long press at startup anyway. Next, I enable to choose between two profiles as startup. That means you can save two sets of calibrations, which I find useful. One set for using the SIF socket and one for using probe wires. I did not enable a third profile. In some tests where probes are used, you can show them reversed with colors, which I want to match with my probe wire colors eventually. As it says here, you can assign the colors in the color.h header file. This section is about the measurement of the battery voltage. The standard resistors are correct for my tester, but the default for butt offset is too little. One of these days, when I remember, I need to measure the actual voltage drop and change that value. With the default, it shows a slightly too high battery voltage. Following the parameters that allow fixing the resistor tolerances and some other offsets, I left all of this unchanged, and in the interest of time, leave config.h to move to config_328h. You will be relieved that also config_328h is even larger. Only very few changes are necessary, but they are essential because they match the software to your specific tester hardware. You see, where Karl-Heinz has predefined directories for most kits in the market, with the makefile already set to match the hardware, Marcus has no such thing, and you have to figure it out yourself. If this file is not set correctly, nothing will work, not even the display. The most important part is the LCD display. There are many options. Each option is in a section that is framed with a #if0 at the beginning and an #endif at the end. 0 evaluates, of course, as false, so the compiler will simply skip all the stuff until it finds the endif. By default, the ST7565R display was enabled, so I turned that whole section off by enabling the hash if 0 and the hash endif statement. The display in this kit is an ST7735, so I disabled the hash if 0 and hash endif for that. I could have also changed that if statement to be hash if 1, but I choose to follow the method that was already in use. Unfortunately, enabling the right display isn't enough, and it also needed to change some of the pin assignment. It took me a couple of days to get that sorted, and they are all marked with my name in the comments and what they were originally. The last change is to enable LCD flip X and disable LCD flip Y, because with the default your display image is upside down. Of note, the default font is 10x16 HF. I did not change that, but it will play a role in a moment. There's one more change, which is the pin used for the second connection of the rotary encoder. After all that, you expect me to show how it compiles, but I totally forgot to capture that. But not to worry, I have recorded a second compile. The reason for that will be apparent in a moment. This is the first test of the freshly compiled 1.46M. What language is that? Very strange. The tester seems to work fine apart from the language. This is the main menu, and maybe you already figured it out. I did when I saw FTS, where I would have expected ESR. All letters are simply shifted by one to the right. Anyway, those bugs are the perils of updating soon after a new release. The early bird catches the bug. It turns out some birds were even earlier, and Marcus had already found the error and released a fix. The error is in the 10x16 HF font I mentioned earlier, and Marcus' zip file contains the replacement. The fix is just copying the new file over the old one, replacing it. And of course to recompile. It turns out that the make program did not recognize the font file change and does nothing, because it thinks everything is still up to date. Not in the mood for subtleties, I choose a rather drastic way to tell the make to get to work by deleting all object files produced by the compiler. And of course that does the job. On the statistics, with my selected choice for what's included in the menu, 96.7%, I'm almost maxed out on flash memory, but I have used only 77.1% of EEPROM space. The trouble is of course that most menu options require some of both, so the flash memory is the limiting factor in this case. And with that everything works, of course. Here's an example of how the reversed and color-coded probe indications look. Obviously I need to tweak the color.h file because I want 1 to be red. I should also like 3 to be black, but that would not work with a black background. I need to play around a bit more with the colors, but you get the idea. This video is already too long, but I just want to add one more thing on measuring z-diodes with an external voltage, which I have enabled in the config file. The documentation shows these diagrams, of which only the left one is implemented in my tester. You see where the ground and PC3 connections are. All the right circuit does is to produce up to 50 volts of DC. If you have an external power source, nothing stops you from using that instead. All it needs is a voltage that is higher than the z-diode voltage, but not higher than 50 volts. The crucial point is not to miss R19 on the right. You must not connect the external voltage directly to UX, but only through a 10K resistor. If you miss that, you're not measuring your Zener diode, but destroying it. So the proper circuit to measure Zener diodes looks like this, with a 10K resistor limiting the current through the Zener diode. 10K is quite high and it assumes a fairly high external voltage. I use up to 40 volts. If you are using much lower voltages like 20 or so, you may want to reduce the resistor maybe to 4.7K so that enough current flows through the Zener diode to produce the nominal voltage. Another point, if you use a low voltage Zener diode, for example a 5 volt type, and 50 volts external voltage, the resistor has to dissipate the difference. While a normal 0.25 watt resistor will handle it, it does get quite hot. Better go for a 0.5 watt type. Here's how that looks in reality. I'm feeding an external voltage of 40 volts through the 10K resistor, And you can see the display reading about 13.28 volts when testing one of these 13.3 volt Zener diodes. Marcus is probably busy with new functions for the menu, and I'm planning to build and explore the ring tester function soon, and maybe showing the capacitor ESR and leakage tests in action. So don't forget to subscribe, and if you not have already, maybe consider becoming a Patreon, link in the description. As Patreon you get early access to videos, a blog and other exclusive content. Thanks for watching.